Okay, so this is kind of a supplement to some of the stuff we did in class today, where we discussed basics of stress and strain. Well, I'm sorry, stress. So this is to supplement stress. And what we're interested here is, well, I want to help sort of visualize stress and show that it actually isn't like a homogeneous thing. It's something that varies with respect to position. And hopefully go a little more in depth and hopefully make a little more sense about averaged stress. Now that's both normal and shear versus the actual stress at a point. All right? And now what I'm going to do with this, I'm going to try and illustrate this with an actual part, and we're going to get the stresses, what we're going to call this the stress field at the point, using a finite element simulation. Now I know in this class you haven't seen finite elements. That's a class you take later, but we can use it as a black box. So this is the part I kind of drew up. I drew this up in NX, and this is what we'll do the model on. Or actually, I already did the model, and I'll just show the results up here. You don't really need to see the actual modeling. The way we're going to consider this thing to be loaded and constrained is as follows. So let me bring back up that window. So the part basically looks like this. All right. It's got a hole on this side. And I'm going to assume that it's fixed. Possibly it's welded. If I wanted to, I could have probably put in some pinholes and made it seem like it was actually bolted at some actual points, like actually some through holes that might have bolted the component, but let's assume it's welded. Here we have a hole here where there's a screw or a pin, and let's assume that that basically has a net down load acting like this. All right? And when I make the finite element model, in fact, I assume, let's find where we fix this. I'm going to assume that this actually has a radial distribution. So this is actually I've actually modeled this. This is something you can do with finite elements. A more detailed bearing type of load. So you can see it's maximal at this point. It acts in the radial direction. It kind of has this, it's actually a sinusoidal type of distribution. All right, so this is the type of thing you can do with finite elements. You break up the model into a little mesh. You run it into a computer. You define these loads and constraints. Those are the so-called boundary conditions. I made it out of aluminum. Let's not worry about the numbers too much. Again, we just want to visualize what's going on here. And then I run the simulation. And the results are in this part of the model. You see those little triangles. That's the actual discretization that used. And now over here we can actually plot the stresses. The elements, nodal ones are, they're kind of nice because they give a nice smooth result. So this is actually the X. What I'm plotting here is the normal stress in the X direction. So this is the sigma XX component, if you will. So if we go back just to allow me to draw on this, if we were to do a cross-section like we do in class, so that we wanted to actually compute the internal reaction forces, let's say we made a cut somewhere through the body, this normal stress, and this is the X direction, would be, a stress component that acts as follows, right, in that direction. And it varies along the whole surface. And if you look at this, let's look at the side, the top view, to kind of give some. No, actually I had the load going up, so I had this. This actually gets flipped. So, well, here, we'll do this. Make it. There you go. Okay. If you actually look at this, you can see the distribution if you follow my mouse. So on the top side, we have positive stresses, and on the bottom side, we have negative stresses. They're compressive. And actually, through the middle, it about goes through 0. So this, if you look at it, actually has a distribution that kind of looks like the following. I probably should have. So it's, and we'll talk about this later on, and we'll see this is really typical of bending type of stresses. They tend to do stuff like this. Okay? And that's the actual stress distribution. So you can see if I kind of drew a line, and it varies from point to point. So if you go more towards the ring, you can see it's the variance isn't so much. As you get to the root, you see that it switches distribution a lot more. So actually, if I were to look down sort of more at this end, what you see instead here, if I did a cut here, they're much lower and they're kind of positive. So it's more like, it's almost more uniform. So it's almost more like this. So it changes where you are in position. That's actually what's going on in the body. All right. Now, we can also look, I'm sorry, I keep doing this. I keep writing stuff, and I keep forgetting that you guys can't see it. So I guess let's see if we can put this next to each other. Let me restate what I'm saying. I can see all these things, but you guys can't. So here you can see how it varies, and what I've drawn here is how that variance, from looking at the colors, would show up on this plot. And like I said, as you look down closer to the hole, it's more uniform. As you go farther towards the fixed end, it actually becomes more pronounced. Okay? Okay. And actually, in this case, there is a little bit through the 0. Now, all right. So that's the norm. That's looking at the normal stress, the actual point-wise normal stress through the body. And I can rotate it if I can remember how to rotate. And you can see there is some variance through the thickness, but actually not too much. So it's relatively independent of this dimension, but mostly a 2D problem. Now, there are some problems where that might not be the situation. Now, we can also look at the XY stress. This is the shear stress. And we will talk later in this class about why it's called that, so on and so forth. But this is, again, if we go back to the picture we looked at in class, this would be the stress components that act up along this face. Okay? And if you look at them, they are basically they're going close to 0 at the edges, and they go up a little bit in value to about the middle, and then they go back down to 0. There's a max stuff over here. I won't talk about what's going on in here. This is a little out of the scope of what you can get with mechanics and materials types of stuff, but this is why you use finite elements. But let's just look in this region here where it, it's away from the end effects. So it has this sort of maximal distribution in the middle, and we'll talk about it when we talk about stress, but if these are positive values, then on this side, these would actually, if we cut here and looked at this exposed face on this body, these would actually be a down. So let me draw that. So these would actually be down. It's biggest in the middle, and then they kind of get smaller as you go out, and they actually get almost close to 0. Okay? So it has this sort of distribution, biggest in the middle, and it goes to 0 at the ends. Okay? So if you were to plot it, it would kind of look something like that. Okay? All right. Again, those are the actual stresses at the points. These are S, the shear ones, which has units of force per area. And you can see that that's a function of position across the face, across Y and Z, where this is Y and Z is coming out of the board. All right. Likewise, the red ones are the normal. They also have units of force per area. They're the normal ones. And they're also a function of Y and Z. All right. So although I won't do it here, the computer can do it. And you can actually get that precise distribution. Okay? And you can visualize it here. All right. Now let me just go through some of the math a little more and show you how this becomes P over A, basically. All right. So let's talk about the reaction forces. All right, let me get a new piece of paper. That works. So we have some geometry that looks like this. Let's just look at some cross section. It's cut. My poorly drawn diagram. And well, let's talk about the normal. The normal seems to have some sort of distribution that looks like this. It kind of goes a little bit like this. And then the shear has this type of distribution. Okay. All right. And this is the x direction. This is the y direction. And the z direction's out of the board. All right. The net reaction force in the x direction, R. That's this, and let's do something bigger. Okay, that's R. That's the big R force, right? I'm going to call this R. That's the net reaction force. This is the internal reaction force. That's the one in the x direction, the normal one. Okay? And it's equal to the integral over this area. Now the area we're talking about is the area that that these loads act on. So this is the one that I can't really draw very well, but right? This is the area. Okay, I'm going to call that the area. All right? And this is a little differential area. And so it's just, oops. It's the integral of t of y and z. This is t. So T, again, we can think of T as this normal stress at a point. This is what in the finite element model we're calling the sigma XX stress, okay? And this is actually what we'll call it in one of the later chapters when we start talking about this sort of stuff. So that's this normal stress at a point. All right. This is the total internal reaction force, okay? That's a different way of doing it, although we would typically do it with our free body diagrams, but they have to equal this. They have to balance that out. Okay, so I should say this is also what we get from, also sum of forces and sum of moments on the free body diagram, okay? But we're doing it. Okay, and similarly, the I don't have a blue one, so I'll have to do green. There's the reaction force, the shear reaction force. V is the internal reaction force. That's in the y direction. That's due to shear. This is what comes about from sigma xy in the FEM model. Or what we're going to call this, tau xy later on. People use tau for shear just as much as they use sigma. And that is, again, equal to the integral over the area of the actual pointwise traction, which we denoted with S of x, of y and z. So the integral of S of y and z dA, right? So this is really, I think I'm assuming. This is what comes from S. Right? So you can think of S, this actual distribution, as the point shear stress. So this is the pointwise okay? Now those are important actually, and those are really the ones that exist. Those are physically the ones that happen, and if you actually look at this model and you want to know where the worst stresses are, you can see they're actually here and here, you know, and a little bit at the root here and here. And they're actually at these, what we'll call stress concentration points later on. In our analysis at this point in time, we're not sophisticated enough to look at those, but we're looking at these average ones, okay? Okay, so we have the shear stress at a point, the normal stress at a point. This is actually the physical stress that shows up. We can integrate those quantities over the cross-sectional area. That gives us the internal reaction forces, right? Because now these both have units of force, right? That's force. And this has a unit of force. R and V both have force. Now, let's talk about the average stress. So we know, in fact, oh, let me do the moments. I need to do the moments while I'm at it. So let's talk about the reaction moment. So if you look at this, let's get the reaction moment. Here's the internal reaction moment, M, all right? M is the internal reaction moment. Again, this is what we would get from sum of force and sum of moments on the free body diagram. Okay? But it's also equal to the integral of the moments. And now what causes the moments? So again, we're going to integrate over the area. These are little differential moments. What's the differential moment? If you look at this, there's a little differential moment from the traction applied at this point. If you look at it, here we have a moment arm. This moment arm is y, all right? So dm is actually equal to the traction, that's the force, that's the T, times dA, that's the force, or the differential force, and then its moment arm is y. So the actual moment, reaction force, is the integral over the area of T, and that's a function of y and z, times the moment arm y, times the differential area, okay? And you could actually compute those if you wanted to, if you knew exactly those distributions, okay? All right. So once you see this, it's obvious that these are the ones that arise and give you these, you know, these sort of fictitious internal reaction forces. Again, as I kind of mentioned in class, you can argue that these don't really exist in reality, but these are what we use to make the problem a little more tractable. You know, we can understand it a little better in terms of these than these more complicated distributions, right? All right, now let's talk about the stress. And the stress we're going to be talking about in this class mostly is this average stress, okay? And again, we're looking both at normal and shear. Okay, so obviously again, let's first look at the normal. So this value T is really the pointwise normal stress. So if you want to take the average of it, like you would take any average, well, let's call this sigma bar. This is going to be the average normal stress. Okay, so this is going to be the sum of all the pointwise stresses, normal stresses, divided by the total area, right? That's the average, okay? So in other words, it's the integral over the area of the pointwise stresses, that's the T of y and z, okay, times the area, divided by the area. Right? That's the average. Okay, that's mathematically the average. Now, you look at this quantity here, and so you can recognize that that quantity in the numerator, let's get this both on the same page. All right, do this one. Hold on a second. Sorry. Okay, you can see this quantity in the numerator is in fact just the internal reaction force R. So this is actually R, and this is actually the cross-sectional area A. All right? So this is what gives us the fact that the average normal stress is also R over A, where this is the internal reaction force. The one you would get, typically we're going to get this from some moments and forces on the free body diagrams, and this is the cross-sectional area. All right? Now we could do the same thing for the shears. That's going to be the average shear stress. All right? And again, that's going to be the integral over the area of the point shear stress, which is the S dA over the area. All right? And then if you look at this, you can see that the numerator here is the internal reaction shear force, V. So this is V. So this gives you that the average shear strain is V over A. Okay? So this is the internal shear reaction force. All right? And so to kind of just go with this a little bit more, when you so these are important, right? These are boxers. You got to box these guys. You remember those, okay? And you have to remember the concept, right? Think of this picture. Maybe not that picture. Think of this picture. Right? Okay, so although these come about from the actual pointwise stresses, you can get the averaged ones by just force over area. Okay, and now when you're talking about normal or shear, the difference is which force are you using, the normal or the shear force. But actually the area they act over is the same. We'll do a couple other ones in class. Usually people understand the area for the normal, but sometimes there's some confusion about the area used for the shear. But you can always see that the shear has to act along a face. So the normal stresses, they tend to take a thing like this and elongate it, right? Shear stresses tend to take a block and shear it as follows, okay? And we'll talk about that when we talk about strain a little more, but that's kind of the modality. You're talking about a stretching, do this, a stretching, get something more compliant, versus a shearing. I don't have anything better. I need something more stretchy, but I don't have anything. But that's the idea, right? Stretching versus the shearing, okay? Okay, I think that's probably about, well, just one other thing, and then I'll stop. But again, just so you should know, when we look at, find it, comparing the values of the average ones versus the pointwise ones, what you'll find is the point stress values will actually, in regions, be greater than the average. Okay, so actually, if you look at this and we integrate this function, you can see you have a little bit more positive area than negative area, right? So this actually will be a value r that's something like that. We divide by the area. This peak here will be less than that peak. So it gives you a less conservative value. All right. Again, you can look at the body and you can see here, we get maximum minimal points that vary a little bit. Okay. Okay. We'll talk about that later. Okay. Actually, when we go to bending, you'll see that there's a refinement we do on here to capture the bending stresses more accurately. But this is just a simple example to show you this visualization in class. Okay. So it's fine from now on to remember these stresses as force per area, but really remember that don't lose sight of the fact that they're actually point-wise values, and they vary across the cross-section. Okay? All right. I hope that helped.